Hello lovelies, in this video we're going to be going through the A-Level Maths paper 1 that we've written for 2024. Now the really important thing with this paper is to watch how we've structured our answers. How are we showing off to the examiner that we know everything that we do know? So after the question comes up, what I want you to do is to pause, have a go at it yourself on a bit of paper, and then check with Charlotte that you've actually managed to answer the question correctly and get all the marks. She's going to show you some really fantastic hints and tips to really get you good grades.
Point A has the position vector 4i minus 2j plus z, and point B has a position vector of 5i minus 2z. And we're asked to find the magnitude of AB. And that's what these two lines on either side mean. They mean that they want the magnitude, which is the size or the length of this vector. The way that we do this is by using Pythagoras' theorem. But in order to do that, first off, we're going to have to find out what the vector of A to B is. So that's going to be our very first step, finding the vector of A to B. So to find this vector A to B, we have to do B minus A. I always remember it's just the opposite way around. You may also see this written as O to B minus O to A. They mean the same thing. So in order to do this, I'm going to rewrite these vectors as column vectors, where the I component's at the top, the J component's in the middle, and the Z component is at the bottom. So for this reason, this B minus A, we can rewrite this now as 5, 0, minus 2, minus 4, minus 2, 1. The reason why I personally prefer column vectors is because it's very visual. I can completely see the comparison between the top bits, the middle bits, and the bottom bits. Whereas otherwise I'd have to think, oh, which is the I, which is the J, which is the K. I don't know. It's not that big, it's not that different. Whichever method you feel most comfortable with, I just quite like using column vectors because it feels quite nice and neat and organised. So let's get started. Starting with the tops, I'm going to do 5 minus 4. Then for the middles, I do 0 minus 2. And on the bottom, I do minus 2 minus 1. So now let's simplify this. 5 minus 4 is 1. 0 minus 2 gives me positive 2, and minus 2 minus 1 gives me minus 3. So we could at this point put this back into the regular notation for vectors, and we can say that the vector of A to B is equal to 1i, or just I, plus 2j, and then minus 3z. And there we have the vector of A to B. So now we've done this, we can get on to our second step. For our second step, we need to find the magnitude of A to B. And like we mentioned before, that involves using Pythagoras' theorem. However, you don't have to think about this too deeply, okay? Just take the coefficient of the I, square it, add the coefficient of the J, square it, and add the coefficient of the Z, and square it. And of course, you can then finish off by square rooting it to get that magnitude of A to B. That gives us 1 squared plus 2 squared plus minus 3 squared, and then you square root it. So that leaves us with the square root of 1 plus 4 plus 9, which is equal to the square root of 14. And that there is our answer. That is the magnitude of A to B. Here we're asked to solve e to the 10x equals 5e to the 5x minus 6, giving your solutions to 3 decimal places. Well, this is what I like to call a hidden quadratic equation. We should recognise that the powers of these exponentials, or powers of anything in a question, are in the ratio of 2 to 1. And when that's the case, it generally means it's a quadratic. So first things first, let's just move across everything so that it's on one side. So I'm going to start by subtracting the 5e to the 5x and adding the 6 to then be left with this quadratic equation equal to 0. So now I've got e to the 10x minus 5, e to the 5x plus 6 equals 0. So the reason why this is a hidden quadratic is because if we actually had e to the 5x and we squared it, due to our power rules, and when we do the power of a power, we know we multiply those powers. Here, when we do e to the 5x squared, we actually get left with e to the 10x, which is what's in this question. So this means what we actually have here is a quadratic equation, and it's of the form of e to the 5x squared minus 5 e to the 5x plus 6 equals 0. And so this is something now that we can factorise. We can see it's a quadratic equation. We want to have two things that are going to multiply together to give us positive 6, and that are going to add together to give us negative 5. Now, having a little think there, I know minus 2 and minus 3 would work. So I'm going to put e to the 5x minus 3 times by e to the 5x minus 2. Now, if you find that confusing, just so you know, some people use a substitution. Some people say that y is equal to e to the 5x, and therefore rewrite our quadratic equation as y squared minus 5y plus 6 equals 0, because visually it looks cleaner and people are more familiar with quadratic equations looking like this. Now, the time when I would recommend using this method is if you're looking at the other equation with the e to the 5x's and you're just confused and you can't visualise how you can factorise that. So what you can do is you could just factorise this as y minus 3y minus 2 equals 0, and then solve it from there. However, make sure that you make that final substitution, that e to the 5x in place of the y, so that you solve it for x at the end. But this is just like a little side thought as to what you can do in these questions if you just can't quite factorise it with the e to the 5x. But anyway, let's get back to the question. So because this whole thing equals 0, we know that this first bracket could equal 0. So we can say that e to the 5x minus 3 could equal 0. So what we can do here is we can rearrange this now. We can say e to the 5x could equal 3. And then we can move forward and rearrange this now to get x as the subject. Now the problem that we have at the moment is that the x we want to find is held up in the power. And we need to rearrange it so that that x is no longer in the power. So we need to get rid of that e. Now we need to know what the opposite of e is to get rid of it. And we should know that the opposite of e is, of course, ln, the natural log. So if we do ln of each side, we're just left with 5 to the x on the left, and then we get ln 3 on the right. So now this is much easier. We can get the x on its own. All that we need to do now is divide through by 5. That gives us x equals ln 3 over 5. Now this question wants our solutions to 3 decimal places. So if we pop this into the calculator now and round it to 3 decimal places, I end up getting 0.220. So that is my first solution here. Next up, we need to do the same for the other bracket. Okay, so starting by making a little more space, we can see that e to the 5x minus 2 can be equal to 0.2. So now if we rearrange this, just like we did with the other, we've got e to the 5x equals 2. And if we take ln of each side, we will get rid of the e and unlock the x there, giving us 5x equals ln 2. And finally, just rearranging, we end up with x equals ln 2 over 5, which, to the 3 decimal places that the question requires, is equal to 0.139. And there we have it. There are our solutions to this question to 3 decimal places. With this question, the main takeaway is that, of course, be always on the lookout for hidden quadratic equations within A-level maths. It can come up in lots of different formats, not just e's. It could be 2 to the power of something, 10 to the power of something. It could be in trigonometry too. So just always keep your eye out for it because it's a sneaky question, which is actually just using your GCSE knowledge. If the modulus of x equals 2, find the possible values of the modulus of 3x plus 1. So if the modulus of x is equal to 2, then we have two options of what x could be. X could be equal to 2, and x could be equal to minus 2. So what we need to do is to substitute these one at a time into mod 3x plus 1. So if we do the modulus of 3 times 2 plus 1, then we end up getting a modulus of 7, which is simply 7. Then if we do the modulus of 3 times minus 2 plus 1, then we end up getting the modulus of minus 5. And remember, modulus makes negative values positive, so therefore we get 5. And so those are the possible values of mod 3x plus 1, 7 and 5. Now we're asked to find the set of values of x for which the modulus of 3x plus 1 is bigger than the modulus of x minus 3. So the first thing I'm going to do here is to actually draw a little bit of a diagram, okay? Got my axes here, and I'm going to start off by drawing the modulus of 3x plus 1. So we know that the modulus means that the y values, the outcome of this, cannot be negative. So if we were to imagine that we were drawing, for instance, just the 3x plus 1 line, we know it would intercept at plus 1. It's going to have a gradient of positive 3. However, where it would have gone negative, it reflects in the x-axis. Now what you can see what I've done here is on one side of this line, I have called it 3x plus 1. That's just the regular, what the line would have looked like. But then the other part that has been reflected, essentially, this part here, I have essentially done the unmodulus of that, if that's such a word. I have said, well, if I know the modulus makes values positive, if they were negative, then the negative version of 3x plus 1 is minus 3x minus 1, okay? So this is what the graph of the modulus of 3x plus 1 would look like. So now let's do the same thing with the modulus of x minus 3. So here again, I know that I'm going to have a line which would have intercepted at minus 3, and it's going to have a shallower gradient. It's only a gradient of 1 here compared to the 3x of the other line. It would have intersected at minus 3. However, of course, we know, don't we, that it got reflected in the x-axis at that point. And so I've got two parts of this line. I've got x minus 3 on the right-hand side, and on the left, I've unmodulused it, and I've done the negative version. So that's minus x plus 3 rather than x minus 3. So now I can see here that there's 2 points where this crosses. One of them is a positive value of x, and one of them is a negative value of x. So now we've got the information we need to solve it, okay? Here we can take this line of the 3x plus 1, and we're looking when is it going to be bigger than, and see it cuts this line here, doesn't it? The minus x plus 3. So what I've done here now is I've done 3x plus 1 is bigger than minus x plus 3. I just chose the 2 relevant lines out of the 4 we have drawn. And by arranging that, I end up finding that x is bigger than a half. So that is great, okay? So we've got our first little equality here. Now let's have a look at the other point of intersection here. I can see that it's this region here of the minus 3x minus 1 line that is bigger than the minus x plus 3 line. So we're just picking which lines out of these 4 are the relevant ones to these points of intersection. Now rearranging this, we get minus 1 is bigger than 2x plus 3, which gives us minus 4 is bigger than 2x. And rearranging that, we get that x is less than minus 2. And so those are the points where our modulus of 3x plus 1 is bigger than the modulus of x minus 3. That's one set of methods. Another method we could do is we could square both sides of this. So we could say let's do 3x plus 1 squared is bigger than 3x minus 3 squared. Now let's multiply out the brackets, okay? Don't forget to do double brackets and not just square the individual bits. So over on the left-hand side here, I get 9x squared plus 6x plus 1. And that is bigger than x squared minus 6x plus 9. Now, if I rearrange this to get everything onto one side, I end up getting 8x squared plus 12x minus 8, which is bigger than 0. Now I can cancel down here by a factor of 4, giving me 2x squared plus 3x minus 2, which is bigger than 0. Now factorising this, I put 2x in one bracket. I'm going to put an x in the other bracket. I need a positive 2 and a minus 1. So I factorise that to make 2x minus 1 times by x plus 2 is bigger than 0. Now the reason why that's important is because now we know where it crosses the axis by factorising that. With quadratic inequalities, I always like to make a little sketch of a graph, really rough sketch of a quadratic curve, the smiley face version in this case because it's positive. And I know that I've got a half is one of the roots and minus 2 is the other root. I know that the x-axis is that line of equals 0, and bigger than 0 is going to be above the curve, and that's what we're asked for here. And I've shaded in here the regions of this curve that go above 0. So I can see, if I imagine this like a number line, that is x is bigger than a half and x equals minus 2. Those are our two regions that will satisfy this. So we've got exactly the same as when we did the other method by sketching those straight lines. Either way works, so whichever way suits you best. However, we do need the set notation for this. And it will look like this, okay? So we've got x colon, x is less than minus 2. We need to do the union sign because both of these things are true. And then we've got x colon, x is bigger than a half in our curly brackets. So that is the notation that we need to use to be able to get all of our marks in this question. And it's taken a while, but I've shown you two different methods that we can use to solve this. So I hope that made sense. Make sure that you pick whichever method you like the most and get using it. Good work. Here we're told that the function g of x is equal to 2x plus 4 over x minus 3, and f of x is equal to x squared minus 4x minus 4. Here we're asked to find fg4. So this is a composite function, and with composite functions you kind of work backwards. So the first thing we want to do is substitute 4 into g to get g4. So to do that we just replace every x value with 4. So here we get 2 times 4 plus 4 over 4 minus 3. And so simplifying that, I end up getting 12. So now we know what g4 is, we know that's 12, we can put that into f of x. So fg4 is actually just the same as f12. So now we substitute in x equals 12 into the f of x formula. So like we said, fg of 4 is just the same as f12. So f12 is equal to 12 squared minus 4 times 12 minus 4. And that ends up giving me 92. So fg4 is 92, that's our answer. So now we're asked to state the range of g. And although this is just a one marker, this is something that people really struggle with. So let's have a look at the function here. We know that the domain is when x is bigger than or equal to 4. Now, if we were to draw the graph without that, we can see, because on the denominator there we have x minus 3, we can see we would expect an asymptote when x equals 3. So that means that the curve would look a little bit like this. However, we're just looking at when x is bigger than or equal to 4. So we're not actually looking at that part. But you can see the value of y values that this is existing between. If we take a look at the beginning of this point, when x is equal to 4, If we find this y value, then we can find the upper limit of the range. So if we substitute into G 4 and do 2 times 4 plus 4 over 4 minus 3, which we already did in part A, we get 12. So that there is the y coordinate when x is equal to 4. And if you look at the shaded region, that is the biggest value of y that we have there. After that, you can see we have another asymptote, but we're not quite sure where that asymptote lies. We need to find that out. The way that we can do this is we can have a look at our function. So we know our function is 2x plus 4 over x minus 3. And if we imagine that x is tending to infinity, we're getting really big, really big, and we look at this equation, we can see 2 times a really big number plus 4, and then divided by a really big number minus 3. The 4 and the 3 just don't matter anymore. We can just ignore them. And we can see that essentially simplifies down to 2x over x. And those x's can cancel. So that means that the asymptote here is going to be at 2. So we know on the upper end of this range that g is going to be less than or equal to 12, but because of this asymptote, it's going to have to be bigger than 2. It never will actually be 2 because it's an asymptote there. However, it will be bigger than 2. So that is our range of g. So now we're asked to find the inverse function of f and state its range. Remember, that's what f to the minus 1 means. Some people confuse it with differentiation, but it definitely means do the inverse. So here we've got f of x equals x squared minus 4x minus 2. And my top tip to you is whenever you need to find the inverse of a quadratic, is make sure you complete the square first. Okay, so we're going to need to complete the square of this function. If we don't complete the square, we're simply not going to be able to rearrange this to get x as the subject as we're going to need. Okay, so let's start off with this then. See that I've replaced the f of x with a y, because that's how we do that when we're working out the inverse. Now to complete the square here, I am going to look at my coefficient of x, and I am going to halve it. So I write x minus a half of that minus 4, so minus 2. I'm going to put a little squared up in the air, and then I'm going to subtract the square of that minus 2. So I'm going to subtract 4. Then on the end, I just plonk that other minus 4, and I have my completed the square version, which I can tidy up a touch. I can say y equals x minus 2 squared minus 8. So there we have it, we've done that part. However, we now need to actually work out the inverse. So the first thing to do when working out the inverse is we swap over the x's and the y's. So here we have x equals y minus 2 squared minus 8. Next we want to rearrange it to get the y as the subject. This may seem weird, but remember this whole method is just a trick to get the inverse. Okay, so getting started with this rearranging, if I shift that minus 8 onto the other side, I get y minus 2 squared equals x plus 8. So now let's square root both sides. I get y minus 2 equals the square root of x plus 8. And then finally, let's add 2. So that gives me y equals x plus 8 square rooted plus 2. So the last little finishing touches now. Replace the y with f minus 1x, because that's what they were asking for. They didn't just want I, they wanted the inverse function. Next up, remember that we're being asked to state the range of this inverse function. To answer this, we must remember that the range of an inverse function is just the same as the domain of the function. Now we were told on the previous page that the domain of f of x was x is bigger than or equal to 2. Now if we simply replace the x with y, because range is talking about the y values, we can just say that the range is y is bigger than or equal to 2. So finishing up here, we're asked to describe the relationship between the graph of the function f of x equals x squared minus 4x minus 4 and the graph of its inverse. Now this is just a nice easy fact that we need to go away and memorise. We should note that they are the reflection of each other in the line of y equals x. And that's all you need to know. So it's a really easy mark to get if we just go away and learn that fact. When metal spheres are heated, they expand. The volume of a sphere increases at a constant rate of 0.2 pi meters cubed per minute. Here we're asked to show that dr dt equals 1 over 20 r squared. So looking at this, it's a show that. I always say with a show that, don't stress too much about the outcome. Let's just think about what we know. So we're told that the volume of the sphere increases at a constant rate of 0.2 pi meters cubed per minute. Now, because it's volume and it's rate, that means it's dv dt, and that is equal to the 0.2 pi. Of course, it's increasing as well. That means that it's a positive. If it said decreases, we'd make that negative. So other information that we know in the question is we're talking about volumes of spheres. We should know that the volume of a sphere equals 4/3 pi r cubed, and therefore we're able to differentiate that with respect to r this time, and would multiply through by the 3 and then lower the power to be left with 4 pi r squared. At this point, we've really done all we can with the information we know. So we'll glance over at the show that, and we can see it says dr dt. So if I look at what I have, I can kind of construct that using the chain rule. If I do dv dt and I multiply it by dr dv, I can see that the dv parts here will cancel out, and we would just be left with dr dt, which is exactly what we want. So that means that this is how we're going to work out dr dt. Now the dr dv part of this we should recognise is just 1 over dv dr. So it's the reciprocal of the dv dr that we found out. So dr dv is equal to 1 over 4 pi r squared. Now we can just multiply these together. So dr dt is equal to 0.2 pi times by 1 over 4 pi r squared. So if we simplify this now, the pi's will cancel, and 0.2 divided by 4 gives us 1 over 20. And so as a result of that, we get 1 over 20 r squared. And that is what we were being asked to show. So there we are, we've finished part A here. So after 20 minutes, the sphere has a radius of 1.5 metre. Here we're asked to find the radius of the sphere after 1 hour of being heated, and we need to give your answer to 2 decimal places. Now the reason why I've written down this equation from part A is because whenever you have a show that, we're going to need it later. And that's the great thing about show that question, because even if you couldn't do part A, do not let it stop you doing the rest. They've given you the key to the rest of the question. So in this question, we need to find the radius, which means we need to turn this into an equation in terms of r and t. Now the way that we're going to do this is by first separating the variables. So we want to get all the r's and the dr's on one side and all the dt's on the other. So first things first, I'm multiplying through by the r squared. Here I've got r squared dr dt equals 1 over 20, and then I'm going to multiply through by the dt. That gives me r squared dr equals 1 over 20 dt. You could have moved the 22, it's all going to work out the same. I just chose to leave it there. So now we've separated the variables, it's time to integrate. So I'm integrating both sides of this equation. When I integrate r squared with respect to r, that just becomes r cubed over 3. And when we need to integrate 1 over 20 with respect to t, remember that 1 over 20 is just a constant. It could be any odd number, it could be 2, it could be 3. When we integrate a constant, we just introduce that variable, so this time it's going to be 1 over 20t. And because there's no limits on our integrals here, I'm going to put on a plus c at the end of this. So maybe you're thinking, why don't we put a plus c next to the r cubed over 3 as well? Well, we just don't need to. A constant's a constant, and the constant I've written down here is actually absorbing both of these constants. So that is good enough. We will leave that there to keep things simple, and we'll go on to the next part. So the next thing we need to do is make some substitutions so that we can find out what that constant is. So we're told that after 20 minutes, the sphere has a radius of 1.5 metres. If we remind ourselves from the earlier part of the question, we were told dV/dt was measured in the unit of metres cubed per minute. Now that means we can keep this 20 minutes as it is. We don't need to convert it into hours or seconds or anything. So when we go to our equation that we just found in our second step of our working, where we said r cubed over 3 equals 1 over 20t plus c, we can substitute in 1.2 in place of the r, and in place of the t, just 20. So here we have 1.5 cubed over 3 equals 1 over 20 times by 20 plus c. So putting some of this into the calculator now, I get 9 over 8 equals 1 plus c, and therefore c is equal to 1/8. So now we have this completed equation in the order that we need it. Okay, so we've got r cubed equals 1 over 20t plus 1/8. This is going to enable us to work out the radius at 1 hour. However, like we mentioned earlier, this equation is using minutes. So we need to convert 1 hour into minutes. So t will equal 60. So substituting this in, we get r cubed over 3 equals 1 over 20 times by 60 plus 1/8. So now we need to solve this for r. Rearranging this, putting it into the calculator, timesing by 3 and then taking the cube root, gives me an answer equal to 2.108581663. Now the question wants it to 2 decimal places though, so here we have that the radius equals 2.11 metres. And that there is your answer. So make sure that you're familiar with the need to separate the variables, integrate, and then make substitutions to find the value of c. Find the rate that the surface area of the sphere increases in this sphere when r equals 2 metres. Here we're asked to give your answer to 2 decimal places. So here we need to remember what the equation for the surface area is. So if you don't know these basic facts about spheres or lots of other shapes as well, make sure you get learning them. So the surface area of a sphere is A equals 4 pi r squared. And now that we have that, we can differentiate that. We can find out what dA dr is. And that is equal to 8 pi r. Now we know from earlier in the question that dr dt is equal to 1 over 20 r squared. Now the reason why we're thinking about these is because we need to find the rate that the surface area increases. Now remember, rate is always talking about time, and we're talking about the surface area, so we're being asked to find what dA dt is. Now like in part A, we can use the chain rule to do this. We can say that dA dt is going to be equal to dA dr times by dr dt. That's because the dr's would cancel, just leaving us with dA dt. Well, we have 2 equations for these, don't we? We know that dA dr is equal to 8 pi r, and dr dt is 1 over 20 r squared. So simplifying this now, I can cancel out an r, and I get left there with 8 pi over 20 r. So going back to this question, we specifically want it when r equals 2 metres. So substituting that in, I get 8 pi over 20 times by 2, so 8 pi over 40. So if I put that into the calculator, I get 0.62831, and then I need to round it to 2 decimal places. I can see if I round this to 2 decimal places, I need to round up to 0.63. And that there is our answer. That's the rate that the surface area of the sphere increases when r equals 2 metres. So now we need to state an assumption that's been made when modelling the rate of increase of the surface area of the sphere. So for this we need to have a think about the scenario. Remember that this question here was looking at a sphere that was getting heated up and expanding as a result of that. So it's getting hotter. And so what we've had to assume here is that the sphere continues to expand at the same rate as it gets hotter. It's not going to get hotter and then start expanding at a faster rate or something. We're assuming that this is constant and not dependent on temperature, okay? So that there is our assumption. They're always a bit tricky, but always have a think of the wider scenario that the specific question is asking about and see if you can pull in some of that knowledge. Good work. The diagram shows a sector AOB of a circle with centre O and radius R. The angle AOB is theta radians. The arc length AB is 14 centimetres and the area of the sector is 56 centimetres squared. Here we need to find R and theta. Now to do this we need to know a couple of equations. We need to know that the arc length, S, is equal to R theta. We also need to know the equation for the area of a sector A is equal to a half R squared theta. Now in both of these equations theta has to be in radians. So now we have a set of equations, we can start to make some substitutions. We know that the arc length is equal to 14, so we can say that R theta equals 14. We also know that the area of the sector equals 56, so we can say that 1/2 R squared theta equals 56. Now what we have here is a pair of equations that we can solve simultaneously. So what I would probably do here is I would rearrange this first equation to get theta as the subject. Here I find that theta equals 14 over R. If I now substitute that into the second equation, I get a half R squared times by 14 over R equals 56. So now if we cancel out one of the R's and also multiply the half by the 14, we get 7R equals 56. Now rearranging this then and doing 56 divided by 7, I get that R equals 8. So now we know that R equals 8. We can substitute that into one of our earlier equations. We said that theta equaled 14 over R, so here we have theta equals 14 over 8, which simplifies down to give us theta equals either 7 over 4 or 1.75 radians. Here we're asked to find the area of the segment bounded by the arc AB and the chord AB. So here we can see it's this region of our shape. And looking at that, we can see that to get that, we can take the area of the sector and subtract the area of the triangle. Let's remind ourselves of what information we already know. We worked out that theta equals 1.75 radians and R equals 8 centimetres. So we're going to use those to work this out. We were also told in part A that the area of the sector equals 56 centimetres squared, so we don't need to calculate that again. So what we do need to calculate is the area of a triangle. Now because this isn't a right angle, we're going to use the equation a half AB sine C, which in this case, because the two sides either side of the angle are R and the angle's theta, it's going to be rewritten as a half R squared sine theta. So now we've got that equation, we can start making some substitutions. The area of that triangle is going to equal a half times by 8 squared times by sine 1.75. Now a really big point here, this is where you'll make a mistake. Make sure your calculator is set into radians, otherwise you're going to get a completely wrong answer. So making sure we use radians and putting this into the calculator, I get an area for the triangle equal to 31.4875503. So now that we've done that, if we now think of this area of this shape that we need, we can work it out by taking the 56, that area of a sector, and subtracting the area of the triangle. So when I put that into the calculator, I get 24.5 if I round that to one decimal place. They haven't stated how we should round that, so long as we round sensibly and we state to how we rounded it, we will get all the marks. And so there we have it. The main takeaways from this question is make sure that you know the equation for arc length, for the area of a sector, and make sure that you're very careful with these questions. If you need to calculate the area of a triangle, that you use radians. Express 2 sine theta plus cos theta in the form r sine theta plus alpha, where r is bigger than 0 and alpha is between 0 and pi over 2. Give the value of alpha to 3 decimal places. So because they ask us to put it in the form r sine theta plus alpha, let's start off by looking at the formula booklet and reminding ourselves of what this addition formula looks like. So the formula booklet will likely say it in terms of a and b, but we just replace them with theta and alpha. So sine theta plus alpha equals sine theta cos alpha plus sine alpha cos theta. And with there being an r in front, we just stick some r's in front of everything. So what we want to do here is we want to try and compare what we've just said, this r sine theta cos alpha plus r sine alpha cos theta, with our 2 sine theta plus cos theta. So I'm going to write it directly underneath. So what I want us to do here is to make a comparison. So we can see that we've got these sine thetas in both these. That must mean then that the 2 that the sine theta is multiplied by is equivalent to the r cos alpha that the above equation is. We can do that same thing now with the second part of this. I can see that they both have cos theta. So therefore, although we can't see anything next to the cos theta, it's multiplied by 1. So that 1 is going to be equivalent to the r sine alpha in the above equation. So now we know that 2 is equal to r cos alpha and 1 is equal to r sine alpha. Now we know that sine over cos gives us tan. So if we do r sine alpha over r cos alpha, that simplifies just to tan alpha. And so that is equal to the 1 that the r cos alpha is equal to over the 2 that the r cos alpha is equal to. So we know that tan alpha is equal to a half. And so by doing inverse tan of that, making sure your calculator's in radians, because the question says it has to be between pi over 2 and 0, we end up getting that alpha is equal to 0.3636, which to 3 decimal places will round up to 0.464. And so that's our answer there. Next up, we need to work out what r is. And to work out with r, we've got a little trick to use here, and it's essentially using Pythagoras' theorem. We're going to say that r squared equals 2 squared plus 1 squared. So we just square each of those respective terms and add them together. So that gives us r squared is equal to 5, and therefore r equals the square root of 5. And there we have it. In the form r sine theta plus alpha, we have root 5 sine theta plus 0.464. All we need to do with these questions is remember that we're going to use that tan identity to work out what alpha is. And we always do this idea of Pythagoras' theorem to work out what r is. You might be thinking at the minute, why does that work? I'm just going to say, don't worry too much. The reasoning is because when you square both sides, you end up with r sine squared alpha plus r cos squared alpha. And of course we know that sine squared alpha plus cos squared alpha equals 1. So really we do have some simplification going on there. However, the chances of them asking you to show any derivation there, like why that's the case, are very low. And so if you just keep it in your head that it's just this simple idea of essentially doing Pythagoras' theorem with, in this case, the 2 and the 1, you've got such easy marks. It's not actually worth the overthinking of that. But the reasoning is if you square both, you get the sine squared and the cos squared, which we know add together just to make 1, so it just goes away. Okay, so we've done that here, and now we're going to see in the next part a very, very common type of question that follows these r sine theta plus alpha questions. A swimming pool at a water park has a wave machine. A model was developed to show the height in meters of the wave at different times in minutes. So this here is our equation And we can see that t goes between 0 and 12. So calculate the maximum depth of the swimming pool when the wave machine is on and find the value of t when the first maximum occurs. So what we need to do to be able to solve this question is to spot the similarities with our previous question. In our previous question in part A, we had 2 sine theta plus cos theta. Now, if we look at this here, we can see it's somewhat similar. We've got that 2-to-1 ratio between the sines and the coses. However, of course, in this new equation, the H equation, it's essentially been halved, hasn't it? Also, we can see that theta has changed. Theta is now the same as 7 pi t over 25. And we've added something onto this as well, haven't we? We've added on the 1.8. So let's just replace theta with 7 pi t over 25 so we can see this more clearly, see this comparison much more obviously. I can see that what we worked out in the first part is going to be double essentially this. So if we halve it, now we're getting closer to having what we need here. So let's remind ourselves of what we got in part A. We said that 2 sine theta plus cos theta was the same as root 5 sine theta plus 0.464. So if we replace that theta with 7 pi t over 25, we can say that that blue circled region in our equation is equal to 1/2 times by root 5 sine of 7 pi t over 25 plus 0.464. Okay, so that there is just that region that I've got the blue circled part. To get the full equation for h, we're just going to add 1.8 onto that. See how we needed our answer from part A to rewrite this. Now this question wants us to calculate the maximum depth of the swimming pool. And quite often in maths, when we talk about maximum, we think of differentiation. But when we've got sines or coses, we can use the fact that the maximum value that sine can ever take is 1. And so here we just need to make that substitution in this equation that we've got of 1 for that sine part. That gives us h equals 1.8 plus 1/2 of root 5. So if we pop this into the calculator, we get that h equals 2.918 metres. So we found that maximum depth of the swimming pool. We're also asked to find the value of t at which that first maximum occurs though. So if we think about what we use to work this out then, we use the fact that sine of 7 pi t over 25 plus 0.464 is equal to 1. Okay, so that's a little equation that we can set here and solve. So I'm just writing that down. Sine of 7 pi t over 25 plus 0.464 is equal to 1 when we have a maximum. If we do the inverse sine of this, remembering to keep it in radians, the presence of all these pi's gives us a good hint that we need radians, we get that 7 pi t over 25 plus 0.464 is equal to pi over 2, because the inverse sine of 1 is pi over 2. Now rearranging that, I get 7 pi t over 25 is equal to 1.106796. Now rearranging this to get t on its own, I just need to multiply through by 25 and then divide by the 7 pi that we have there. That ends up giving me that t is equal to 1.258 minutes. And there we have it. That is the value of t when the first minimum occurs. It's always worthwhile checking that that is within the range of values that we are told that it has to lie within. We know above that it says that t is bigger than or equal to 0 and less than 12. And of course 1.258 minutes is within that region. So we are good. The wave machine was turned on at 12 p.m. Calculate the first time after 12 p.m. that the height of the water in the swimming pool reaches 1.5 metres, giving your answer to the nearest minute. So what we need to do here is to take our equation for h, the rewritten version, where h equals 1.8 plus a half of root 5 sine 7 pi t over 25 plus 0.464, okay? That's the version we're going to use because we've just got one sine in it. We don't have some sines and some causes all over the place that would make it impossible to solve. So we've got that equation, and in place of h, we're going to write 1.5 because we're looking at the point when the height reaches 1.5 meters. So now all that we need to do is rearrange this. So we need to get t as the subject eventually. So let's chip away at it bit by bit here. If we take that 1.5 and subtract 1.8, multiply through by 2 and divide by root 5, we end up finding that sine of 7 pi t over 25 plus 0.464 is equal to minus 3 root 5 over 25, all right? Hopefully you're okay with rearranging at that level. So now if we do inverse sine of this, then I end up getting that 7 pi t over 25 plus 0.464 is equal to minus 0.271657. Now there's going to be other potential solutions there as well, isn't it? We had this negative value of sine, and so you can see it cuts at several points along the curve. That negative value, though, is going to give us a negative time, and we don't want that, okay? So let's use the first positive value. And we can get that by taking pi, which is at this point here, and adding on that 0.271657. Or you could think of it as pi minus the answer from the calculator, as that is something that always works, that method to find the other sine solutions. Whichever method you used, whether it was this or cast, we get 3.413249654 as our other solution. We can discard the negative version because, like I said, we don't have negative times. So we're going to use this 3.41 and we're going to rearrange to eventually get the time on its own. So that means we're going to have to subtract the 0.464, and then we're going to have to multiply through by the 25 and divide by the 7 pi. Now that ends up giving us 3.35 minutes. Now if we go back and check out the question again, you can see that we wanted to calculate the first time after 12 p.m. that the height of the water reached 1.5 meters. So that means this is 3.35 minutes after 12 p.m. That means that the time is going to be 12.03, and we only want to give it to the nearest minute, so we don't need to think that it's 0.35 or anything. We can ignore that. So the time at which the height of water reached 1.5 meters is going to be 12:03 p.m. So now for the final part of this question. Some people complained that the waves moved too fast. Describe how the model could be adapted to slow down the waves. Well, we should recognise that the frequency of the wave is affected by this region here. And this is really all to do with transformations. Remember that if you had something like function of x, and then we change it, imagine we had f of 2x instead, we know that that would stretch it by a factor of a half in the x-axis. Now that would make this wave more frequent, wouldn't it? Because if it was originally like this, then it becomes like that. So we need to think, what could we do to make the wave effectively longer so that it was a slower wave? Well, if we instead made this factor here smaller, so say if it was, I don't know, like a half or something, then that would indeed stretch the wave by, in this case, a factor of 2, for instance. So we can see that if we decrease the factor that the x, or whatever variable we have in this case, is multiplied by, we will decrease the speed of that wave. So if you look at this particular example, t is our variable here, and it's currently multiplied by 7 pi over 25, what we need to do is decrease this factor. So we need to decrease 7 pi t over 25 to a smaller factor to indeed stretch out this wave and therefore have the wave move more slowly, okay? So there we go, that's how we can adjust the speed of waves. We can simply adjust the factor that the variable is multiplied by. Good work. Here we're asked to show that the integral of 3x times the square root of x plus 3 between the limits of 2 and 0 is equal to 36 root 3 over 5. Now, the method I like to use for questions like this, and I think the best method to use if you ever just feel a bit stumped as to what method to use, is integration by substitution. And what I always do when I have a question that I'm going to use integration by substitution for is I look at the trickiest bit of this equation, so in this case this root x plus 3, and I think, how can I simplify that? What substitution can I make that's going to make this look a lot nicer? And the substitution I will make in this case is going to be that u equals x plus 3. So this is going to be what this whole question is going to pivot on. So we know u equals x plus 3. The next thing I'm going to do is differentiate that. So I get du dx equals 1. And so I can say that dx is equal to du if I rearrange du dx to get dx as the subject. Now I'm also going to rearrange u equals x plus 3 to get x as the subject. So that's a really simple thing to do. I'm just going to subtract 3 from each side, and then I get x equals u minus 3. So I've got all the key things I need now to start substituting into the original equation. So our original equation said we want the integral of 3x times the square root of x plus 3 between the limits of 2 and 0 with respect to x. So let's start chipping away and making our substitutions. So here we can see that the x plus 3 is u. We can see that x we can rewrite as u minus 3. And dx we can rewrite as du. We've got all of our little chunks here that are going to enable us to make a substitution. So by substituting, we have 3 times u minus 3 times by the square root of u du. Now there's one thing we still need to substitute though, and that's those limits. We can't keep using 2 and 0 because those are x values. We need to substitute them into our equation, u equals x plus 3, to find what their equivalent u values are. So when x equals 2, u is going to be equal to 2 plus 3, which equals 5. So our upper limit is going to be 5. When x equals 0, u will equal 0 plus 3, which just gives us 3. So our lower limit is 3. So we replace those limits with 5 and 3, and now we have something that we can simplify and integrate. Well, the first thing I'm going to do is to rewrite the square root of u as u to the power of a half. So here we have 3 times u minus 3 times by u to the half. Now, a lot of people get confused by this. It's almost too simple. Just multiply out the brackets. So here we have 3u minus 9 times by u to the half, which is the same as 3u to the 3 over 2 minus 9u to the half. The reason why that's the case is, of course, where we have the 3u there, that is essentially 3u to the power of 1. And so when we times it with u to the half, we add those powers, giving us 3u to the 3 over 2. So now we have just a really regular, straightforward polynomial that we can integrate by using our normal rule of we add 1 to the power and then we take 1 away from the power. So let's do that then. Let's make a little space. So this integrated is going to give us 3 times by u to the 5 over 2 divided by 5 over 2 minus 9u to the 3 over 2 over 3 over 2. And that's between the limits of 5 and 3. So now, in order to get the value for this, we want to make the substitution of the 5 and the 3. Before we do that though, let's just simplify a little more. 3 over 5 over 2 ends up giving us just 6 over 5. So let's replace that with that just so it's a bit tidier. So here we've got 6u to the 5 over 2 over 5. And then the 9 over 3 over 2 ends up giving us just 6. By all means use your calculator to simplify that. Just don't put the u's in obviously, just do 9 over 3 over 2 and it will give it to you. No point getting muddled in your head. So now that we've done that, we can just put in our values 5 and 3. So what we do is we put the upper limit in first. So we have 6 over 5 times by 5 to the 5 over 2 minus 6 times by 5 to the 3 over 2. And then we subtract it with the lower limit in. So that's 6 over 5 times by 3 to the 5 over 2 minus 6 times 3 to the 3 over 2. So now we can just put this into the calculator. This gives me 36 root 3 over 5, and that of course is our answer. So because it's to show that, you will always know if you've made a mistake. If you don't get that same answer that we need to get, then the most obvious places to go back over and check is firstly, have you integrated correctly? Secondly, have you actually changed the limits as well as everything else? And also, did you substitute correctly? Did you make any mistakes? Did you do the upper limit minus the lower limit? Just check that all of these things were done correctly. Just go back over your work, and if you made any mistake, that's the power of a show that. You know you have full marks if you get to the end of this and you have that show that, which would be an amazing feeling to have. But hopefully that was clear. If you feel a little bit unsure on integration by substitution, then please do just go and try some more examples. In a geometric series, the first term is A and the common ratio is R. The third term of the geometric series is equal to 4 over 9. The sum to the first 4 terms is equal to 5 times the sum of the first 2 terms. Here we're asked to show that the sum of the first 5 terms is equal to 31 over 9. So to do this, we need to start to set up all the information that we know. So the general equation for the nth term states that an equals a times by r to the power of n minus 1. Using this, we can write down an equation for the third term. We're told in the question that the third term of the geometric series is equal to 4 over 9. It means that a3, this third term, is equal to a times by r to the power of 2, because 3 minus 1 is 2. So ar squared equals 4 over 9. So now that we've done that, let's look at what other information we can set up. The rest of the question talks about the sum. So let's remind ourselves of the sum equation. We should know that Sn equals a times by 1 minus r to the n over 1 minus r. And in this question, we're told that the sum to the first 4 terms is equal to 5 times the sum of the first 2 terms. So let's write down something to represent this. So we can say that the sum of the first 4 terms equals 5 times the sum of the first 2 terms. S4 equals 5S2. Now let's get equations for each of these. So using our sum equation, we can say that S2 is equal to a times by 1 minus r squared divided by 1 minus r. And in the same way, we can say that S4 is equal to a times by 1 minus r to the 4 all over 1 minus r. Now we can substitute this into the little equation we wrote down earlier that said that s to the 4 equals 5s to the 2. Substituting that in, we get a times 1 minus r to the 4 over 1 minus r is equal to 5a times by 1 minus r squared over 1 minus r. So now we've done this, we can do a little bit of simplification here. I can see that both of the S2s and the S4s have this factor of 1 minus r underneath them, and they also have a factor of a. I can cancel those out then, and this is going to look much, much nicer. I'm now left with just 1 minus r to the 4 is equal to 5 times by 1 minus r squared. Now 1 minus r to the 4 is actually the difference of two squares. We can factorise this. Because both 1 and r to the 4 are square numbers, we can factorise it in this way by writing a set of double brackets and saying, well, what's the square root of 1? And putting that in the position. So I've got 1 and 1 in each of those brackets. And then I ask myself, well, what's the square root of r to the 4? And that is r squared. So in the bracket, I put 1 and a 1, an r squared and an r squared. And because it's the difference of two squares, I'm going to put a negative on one and a positive on the other. Always keep an eye out for this difference of two squares in maths. Comes up in trigonometry, comes up here, comes up everywhere. It's such a common thing to pop up, so do keep your eyes out for it. So back to the question. Because both sides, the left and the right, have 1 minus r squared, we can just cancel those. And now this is really, really simplifying a lot. Because now all that we have is 1 plus r squared equals 5. Now rearranging that, we get r squared equals 4. And then square rooting that, we find that r would be equal to plus or minus 2. But because we are told here that r is positive, we ditch the negative and we just have r equals 2. Now the question wants us to find the sum of the first 5 terms. So in order to do that, we need to know what a is as well. And this is where we return to that first statement that we wrote. We know that ar squared equals 4 over 9. So if we substitute in place of the r2, we have a times 2 squared equals 4 over 9. Now that leaves us, rearranging it, just a equals 1/9. So now we know r, and we know a, and we know the sum equation. So the sum of those first 5 terms is going to be equal to a times r minus r to the 5 over 1 minus r. Substituting in now our values of a and r, we have s5 equals 1/9 times by 1 minus 2 to the 5 over 1 minus 2. And if I pop that into the calculator, I do indeed get 31 over 9. So I have shown that the sum of the first 5 terms equals 31 over 9, and I have my 5 marks. So the important thing in this question is knowing how to relate the sum equation and this nth term equation. Make sure that you're very familiar with the fact that factorising and simultaneous equations come up quite a lot in these series questions. It's never as simple as, oh, I'm just going to plug those things in. So always keep an eye out for other little topics creeping in, particularly those algebra topics, in every one of the bigger topics. A curve C has the equation y equals x squared minus 5x minus 12 root x. In this question, we're asked to find the differential and the double differential. So let's start by just reminding ourselves of how we differentiate polynomials. We should remember that if we had a function of the form y equals x to the n, then dy dx, that differential, is equal to nx to the n minus 1, which in English means we're going to multiply through by n and then take 1 away from n. So that is our dy dx. Let's apply it now to this particular equation. Let's start by just writing out the equation again. So y equals x squared minus 5x. Instead of writing minus 12 root x, we're going to rewrite this as a numerical power. We should know that root x is the same as x to the power of a half. So that's minus 12 x to the half at the end. So now let's take this one at a time. So when we first differentiate x squared, we're going to multiply through by the power and take 1 away from the power. Now that gives us 2x. Next up, we need to differentiate minus 5x. Now whenever we have just an x term and we differentiate it, we should recognise that we just want to ditch the x essentially. So minus 5x differentiates just to minus 5. Next up, we need to differentiate the minus 12x to the half. To do this again, we need to multiply through by the power and then take 1 away from the power. So when we do minus 12 times by a half, we end up getting minus 6. And when we take 1 away from a half, we get minus a half. So that final term is minus 6x to the minus a half. So now we've got our dy dx. Now we're going to need to differentiate again to get this double differential. So starting now with 2x, because that's an x term, that will differentiate to just 2. Next up is the minus 5. Now minus 5 is of course a constant, and when we differentiate a constant we just get 0, so that's not going to give us an additional term here. And now differentiating the minus 6x to the minus a half, we need to multiply the minus 6 by the minus a half, which gives us positive 3, and subtracting 1 from that power gives us a power of minus 3 over 2. Be careful whenever there is a negative power, when we subtract 1, remember it's getting more negative. I think that's a really easy mistake to make with these fractional powers and the negative powers too. So the answer to this, dy dx, is 2x minus 5 minus 6x to the minus a half, whereas the double differential, found by differentiating dy dx, is equal to 2 plus 3x to the minus 3 over 2. So now we need to verify that C has a stationary point when x equals 4 and determine its nature. And because this is a verify question, we just need to double check. We don't need to prove it. We should know that when we have a stationary point, or a maximum or a minimum, dy dx, that differential, will equal 0. So because we're asked to verify that there's a stationary point when x equals 4, what we can do is we can just substitute x equals 4 into our equation for dy dx and see what it equals. If it does indeed equal 0, then we have verified that there is a stationary point when x equals 4. So let's do that then. So in place of dy dx, we've got 2 times 4 minus 5, and then minus 6 times by 4 to the power of minus 1 over 2. Now, if I pop that into my calculator now, I end up getting 0. So here I have verified that there is indeed a stationary point when x equals 4. So now we need to determine its nature. Now this relies on our double differential. We should recognise that when the double differential is positive, we have a minimum. And when it is negative, we have a maximum. So what we need to do now is to look at our double differential we found in part A and substitute in x equals 4 and see what value we get. So here the double differential will be equal to 2 plus 3 times 4 to the power of minus 3 over 2. Now putting that into my calculator, I end up finding that the double differential is equal to 19 over 8. Now that is a positive value, and therefore the nature of this turning point is a minimum. A curve has an equation x equals y plus 4 times by ln 2y minus 6. Here we're asked to find dx dy in terms of y. Now don't let this confuse you because it's the different way around to how we're used to it. This just means differentiate x with respect to y. So we just need to differentiate as normal. Now, because this is a y term times by another y term, we're going to use the product rule here. So let's remind ourselves of what the product rule is. So in this case, we need to find dx dy. So the product rule will be u times by dv dy plus v times by du dy. So what I like to do now is I like to write almost like a little grid. I'm going to say u equals y plus 4 and v equals ln 2y minus 6. And then underneath each of these, I'm going to write du dy and dv dy. So working out du dy, that's just 1. dv dy is a little bit trickier though. So what we need to do is acknowledge that we essentially need to use the chain rule here, because it's not just ln of x or something, it's ln of 2y minus 6. So what we do is remember what the standard differential is of something of the form ln x. And we know we do 1 over that x then. So in this case, that gives us 1 over 2y minus 6. However, because it isn't just x, it's 2y minus 6, we need to multiply through by the differential of that 2y minus 6. And in this case, that is 2. So we multiply this through by 2. And then we've differentiated that. So now to do the product rule, I like to, once I've laid it out like this, do a little crisscross to let me see what I need to do next, okay? So I'm going to do my little crisscross, and I know that I need to times across those. So what I mean is I'm going to have y plus 4 times by that 2 over 2y minus 6, and then I'm going to add 1 times the ln 2y minus 6, which is just ln 2y minus 6. So I've essentially done it now, I just need to simplify a bit. So simplifying this first term, I have 2y plus 4 over 2y minus 6. Now I can factorise that bottom part here, I can take out the factor of 2. So that becomes 2 brackets y minus 3, and then plus the ln 2y minus 6. If I cancel out these 2's in this fraction term, then I've simplified this as much as I can, and I have found dx dy in terms of y. So now we need to find the gradient of the curve where it crosses the y-axis. Well, let's deconstruct this. When we cross the y-axis, we know that x is equal to 0. And we also know that the gradient of the curve is found by doing dy dx. So not dx dy, dy dx, which is the reciprocal of dx dy. So if we look at the equation that we have, x equals y plus 4 times by ln of 2y minus 6. If this is set equal to 0, I can solve this. I know that either the y plus 4 must be equal to 0, and therefore I could say y plus 4 equals 0 and y equals minus 4, or I can say that the ln 2y minus 6 component must equal 0. So by doing this then, we can then take e of each side to get rid of the ln. By doing that I get 2y minus 6 equals e to the power of 0. I know anything to the power of 0 is actually 1, so I put a little 1 in there. And then if I rearrange this, I end up getting y equals 7 over 2, or 3.5. So now I know those two values of y, where it crosses the y-axis, I can get to work in finding the gradient of the curve. First thing I'm going to do is I'm going to substitute each of those two values into the equation we found for dx dy. So I know that dx dy is equal to y plus 4 over y minus 3 plus ln 2y minus 6. So if I start by substituting in y equals minus 4, I'll get a value for dx dy that I can use to get the gradient. So starting with y equals minus 4, that makes dx dy equal to minus 4 plus 4 over minus 4 minus 3 plus ln of 2 times minus 4 minus 6. Now this first term here ends up going to 0 because minus 4 plus 4 is 0. And then the second part of this gives us ln of minus 14. Now we have a problem there because you can't learn negative numbers. And so therefore we don't actually have a solution when y is equal to minus 4. So we can't move forward any further with that option. So that means that we now need to substitute in y equals 7 over 2. So now let's do exactly the same thing, but this time with y equals 7 over 2. So dx dy is going to equal 7 over 2 plus 4 over 7 over 2 minus 3. And then that's plus ln of 2 times 7 over 2 minus 6. And that ends up giving us an answer of 15. So that's what dx dy gives us. That's great, but we're not quite finished yet, because we're being asked to find the gradient, and we know that the gradient is the reciprocal of dx dy, because we need dy dx. So that means that the gradient dy dx is equal to 1 over 15, and that there is our answer. Here we're asked to differentiate the function f of x equals sine x from first principles and find the exact value of f dash pi over 3. So what that means is we need to differentiate using first principles, and then once we get that differential, substitute in place of x the value pi over 3. To do this, let's start off by writing from our formula booklet what our general equation for differentiating by first principles is. So the equation states that f dash x equals, in the limit where h tends to 0, f of x plus h minus f of x all over h. So that's our equation here. And what I always like to do is not rush into this. I like to start off by writing down f of x equals sine x. So I'm just going to write that down there. And f of x plus h, to get that I now just need to replace the x with x plus h. So I get sine of x plus h. Now this is where we need to do a bit more work, okay? This should look like one of our addition formulas. We learn, and it's given in our data sheet, that sine of a plus b is equal to sine a cos b plus sine b cos a. Well, that is our sine addition formula. So here, of course, instead of a and b, we have x and h. So we can rewrite this now as sine x cos h plus sine h cos x. So that's what we have there. So now that we have this, and we've organised it all, and we took our time, we can make a substitution back into our original equation. So we can say that f dash x equals, in the limit where h tends to 0, sine x cos h plus sine h cos x, and then minus the f of x, the sine x, and that's all over h. So now let's have a think about the fact that this is in the limit where h tends to 0. So where the angle essentially is going to be very small. This is where we now use our small angle approximations. So we should know, and it's given in our formula sheets, that when the angle theta is small, sine theta can be equated to theta, and cos theta can be approximated to 1 minus theta squared over 2. And this is when the angles are small. So here, of course, we don't have theta, we have h instead, but the same will apply. So we can make some substitutions in place of the cos h and the sine h, because h is small in this approximation. So here we have f dash x equals, in the limit where h tends to 0, sine x times by 1 minus h squared over 2, because we don't have theta here, we have h. And that's plus h, because sine h approximates to h, times by cos x, and that's minus sine x, and that's all over h. So now we're going to need to simplify this a step further. So I'm just going to clear a little bit of space here so that we can do that. So now let's multiply out these brackets, okay? So let's do first, what is sine x times by 1? So then we end up having f dash x equals, in the limit where h tends to 0 again. If we do that sine x times 1, we get sine x. And then if we do sine x times by minus h squared over 2, we get minus h squared over 2 sine x. And that's plus h cos x minus sine x, and again, all over h. Now I can see something I can cancel now. I have sine x minus sine x. Now they cancel out, so we can get rid of those here now. We can just scrub those out. Now let's have a go at dividing through by that h. If I divide minus h squared over 2 sine x by h, then I'm left with just minus h over 2 sine x. And if I divide h cos x by h, I'm just left with cos x. So that has simplified there really nicely. So here we have that f dash x equals, in the limit where h tends to 0, minus h over 2 sine x plus cos x. So we've gone as far as we can now. Now we can have a look at that limit of h tending to 0, okay? If h is tending to 0, well, that means that minus h over 2 sine x must also be tending to 0, because it's that h times by the sine x. So if h is going to 0, the whole thing is. That just leaves us then with cos x. So we have differentiated it with first principle. And now we need to find the exact value of f dash pi over 3. So in this case, x is equal to pi over 3. We know f dash x equals cos x, so we just need to find the value of cos pi over 3. Now maybe we've just memorised this, that would be helpful. Then of course we would just know that this is equal to a half, or we could just put that into the calculator. Just make sure that you keep your calculator in radians for when we type in cos pi over 3. Good work though, that is our question solved. So make sure that you know how to use your differentiation by first principles formula, and make sure you know when to use your small angle approximations. A teacher buys a car for £7,500. After T weeks, the car is worth C pounds. The rate of depreciation of C is directly proportional to C. Write down a differential equation in terms of T, C, and a constant K. So, the rate of depreciation is the differential of the cost with respect to time. Rate is always talking about time. So we've got dc dt here. We know that we're talking about depreciation, so the cost is going down. And so we put negative for our dc dt. And we're told that it's directly proportional to c. That's where k comes in. K is our constant of proportionality. So when something is directly proportional to c, we can say it's equal to kc. So in this case overall, we've got dc dt, that's the rate of depreciation, equals minus, because it's depreciating rather than going up, and then kc to show it's directly proportional to c. And that is it, that is our differential equation. So now we're told that the teacher wants to know what their car will be worth in the future. After 4 weeks, the car is valued at £7,450. They realise if they solve the differential equation, they will find an equation for the value of the car, C pounds, as a function of the number of weeks. Here we're asked to solve the differential equation to find the value of the car after 100 weeks. Now the first thing we need to do here, because we're starting with a differential, is we need to separate the variables. So we want all the C's and DC's on one side, and all of the T's on the other. So I end up getting 1 over C dc equals minus K dt. Now that we've got this, we can integrate each side. So here we've got the integral of 1 over C dc is equal to the integral of minus K dt. Or 1 over C will simply integrate to ln C. And minus K with respect to dt, don't forget K is just a constant here. So when we integrate a constant, we just introduce that variable. So here this becomes minus kt. And we have to stick on a plus c because, of course, that plus c is representing the constant from both sides of this equation. So we were told here that they bought the car for £7,500. That means that when t equals 0, sort of initially, the cost was £7,500. So if we substitute those values in here, we end up getting ln of 7,500 equals minus k times 0 plus c. So we just end up getting ln 7,500 equals c. So we know what the constant c is now. We're making good progress. So let's replace that in this equation here. And now we have ln c equals minus kt plus ln 7,500. Now finally, to finish off here, let's use the fact that we know after 4 weeks the car is valued at 7,450. So t equals 4 and c equals 7,450. Let's substitute those values into our equation. So here we get ln of 7,450 is equal to minus k times by 4 plus ln of 7,500. Now that we've got this, we can simply rearrange it, can't we, to get k as the subject here. So a simple rearranging is all we need to do here. Let's get started firstly by moving the minus 4k onto the other side so it becomes positive, and then subtracting the ln 7,450. That leaves us with 4k equals ln 7,500 minus ln of 7,450. Now let's divide by 4 to get the k on its own. So here we have ln 7,500 minus ln 7,450 all over 4. Now popping that into the calculator, I get that k equals 1.67 times 10 to the minus 3. And so now we've got k as well. We've got both of our constants here. So looking at this, I can see that I can substitute that also into my equation for ln c. So let's substitute it in. Here we're going to get that ln c is going to be equal to, and instead of k, I'm going to write minus 1.67 times 10 to the minus 3 t plus ln of 7,500, which we found to be our constant for the integral. So in this question, we're specifically being asked to find the value of the car after 100 weeks. So that's when t equals 100. Let's sub in t equals 100 then. Here we get that ln c equals minus 1.67 times 10 to the minus 3 times by 100 and then plus ln 7,500. So if I put that into the calculator, I end up finding that my value for ln c is equal to 8.755653. So we know what ln c is now, we just need to get c on its own. So to do that, we need to get rid of the ln. So it's important that we know that the inverse of ln is e. So if we do e to the power of each side, we get that c is equal to e to the power of 8.7556583. And simply putting that into the calculator, I get that c equals 6,346 pounds to the nearest pound. And there we have it, that's our answer to B. Assuming the model is correct, find the amount of time it will take for the car's value to halve. Given that 52 weeks are in a year, give the answer to the nearest number of years. So, we know that initially the value of the car was £7,500. So, if the value halves, then that means that the new value would be 3,750. So this is going to be the value of c that we substitute into the equation that we just worked out, and then we're going to need to rearrange it to find t as the subject. So first things first, let's remind ourselves of the equation that we worked out on the previous page. So we said that ln c is equal to minus 1.67 times 10 to the minus 3t plus ln 7,500. So if we substitute into this now, in place of c, 3,750, we get ln of 3,750 equals minus 1.67 times 10 to the minus 3t plus ln 7,500. So if we rearrange that, we get t equals ln of 7,500 minus ln of 3,750 all over 1.67 times 10 to the minus 3. Now, popping that into the calculator, I get 415.058192. So that is how many weeks we have. And we're told here that given that 52 weeks are in a year, find the number of years. So if we divide it by 52, we get 7.981888307 years. In this case, we want it to the nearest number of years. So let's round up and say that t equals 8 years. For the final part of this, we're asked to give a reason why this model may not be correct. Well, the key thing here is that this model assumes a constant rate of depreciation. And so any events that might happen that might really affect the value of that car aren't taken into consideration. For example, perhaps the car could get damaged in some way. So that is the key thing we can say here. And this is something that we can apply to many different modelling questions. So if you weren't sure what to say there, maybe make a note of it, because maybe we can apply this to different types of questions that might come up in your exam.
Oh, well done, lovelies. I'm really, really proud of all of your hard work.